Now that you've learned some of the basic concepts behind TensorFlow, let's jump into using it in a data science experiment. To begin with, let's get a data set that's suitable for classification problems. The Palmer Penguins data set is a curated data set that's been pre-cleaned and is intended as sort of a drop-in replacement for the canonical iris data set. It's got penguins in it. So we're going to be predicting what kind of penguin we're looking at based on the data. In order to get the Palmer Penguins dataset, we can use the TensorFlow datasets package. It's a simple package that makes it easy for us to get datasets into the TensorFlow framework and work with them. The TensorFlow datasets package isn't for importing your custom dataset. It's a utility that lets us get a bunch of reference datasets that are benchmarks or canonical datasets used in the industry, Palmer Penguins being one of them. In order to accomplish this, we just use the tfds load command and we tell it to get us the penguins dataset. It takes care of downloading it, and if you rerun this code, it'll be able to find the pre-downloaded package and cache it so that you don't have to download multiple times. The TFDS package has a get and take method, and that's an easy way for us to grab the tensors that make up our data set. One of the nice things we can do is use the split function that's built into the load method. So if we give it, for example, the train test split at 80-20, as you can see here, the load function will take care of it for us. In order to build our machine learning model, let's use the high-level sequential API. Sequential takes a list of layers and builds our machine learning model in a simple feed-forward neural network. So you can see we're passing just 3 layers to the sequential model here. We have a dense layer, so this is a densely, highly connected input layer, and we're going to give it a ReLU activation function, and we need to give it a particular input shape. So our input shape is one of the easiest ways for us to end up making some errors, and you'll see in future units how the input shape can be debugged. Next, we have our hidden layer. So this is the second layer here. And again, just a simple 10 neuron layer with a ReLU activation function. And finally, our output layers have, as the number of neurons, our number of classes. There are 3 types of penguins in the Palmer Penguins dataset. So we'll have a softmax layer here. And effectively what this lets us do is it lets us say, all right, at the end of our neural network, the highest value is the value that the machine learning model believes is indicated by the data. So if our first layer is the 0th neuron, and our second layer is the first, and our third, all of our labels can correspond to these neurons, and we'll be able to do a simple argmax function to find what is the index of the highest value in this output vector. Note about ReLU, effectively what we want here is to make sure that our gradient does not cause our weights to go underwater. So ReLU will keep us above 0 for the individual values of our neurons. Finally, we need to provide an optimizer and a loss function. Because this is a classification problem with multiple labels, we can pick categorical cross-entropy. It's a categorical problem. And then for our optimizer, we're just picking stochastic gradient descent. The model is ready to be compiled into a TensorFlow computational graph. So we can do that by calling the compile method with our loss and our optimizer. For our metrics, we're just going to put accuracy. And then in order to use our model to make predictions, all we need to do is batch and cache and prefetch. So these are 2 proforma commands, batching and caching, so that we can feed a batch of 8 samples into our data at a time. We can also prefetch our data, and then making a prediction is as simple as calling the model.predict method. You can see that we can iterate through our predictions to understand what the guesses are from the machine learning model for the label of each penguin, that is each sample. And if you want to, you can go through the entire set of labels and compare. That's what we're doing here. This is just a line of code wherein we take the data, that's X, and the label, that's Y, for each item in our test data, and we only want to print the Y, that's the label. And what we end up with is an array of all of the labels. And so we can use that to compare the prediction of any given sample with the label and understand how accurate we're being. Now we can do model training. Because we have very small data, I'm just going to go ahead and batch our data into sets of 32 samples, and we can also cache it in memory. There's also a nice data auto-tuning command that we can run against our data set. That's this here, prefetch tf data auto-tune. But again, here's the simplicity of using a platform at work for us. In order to train our model, all we need to do is call the model.fit method. And we pass it our training data and the number of training epochs that we want for our data set. You can see I've already done that here. It's just stepping through the data, and each time it executes an epoch, the loss is getting progressively less, and the accuracy is going up.